So you may have noticed when we did this problem, there were several points where we had to think about it, just which way do things point? And we had to sort of arbitrarily say, oh, well, it's in the negative x direction or the negative y direction. So sometimes you want a way where you don't have to do that. If that really bothers you, I'm going to show you another way to do this problem. However, it's a little bit risky because it may completely destroy your understanding of electrostatics. You may never recover from this. Okay? So if you're really happy with how we did it in Unit 5, just turn it off. Don't watch. You don't want to see this. Okay? If Unit 5 was just completely enjoyable to you, then stop. But if it bothered you, when we said, well, it's negative, then watch this at your own risk. Okay? To do it this way, we're going to try to do it without all that inspection, all that thinking about which way things point. And to do it, you really have to be really good with unit vectors. So let's look at our unit vector again. For example, let's do r hat 1, 2. So when we looked, well, or we called it 2, 1. Okay, let's do 2, 1. R hat 2. When we looked at it, we had to just think about which way does r hat 2, 1 go. But we can also go with a mathematical definition of r hat 2, 1. Right? Because what was r hat 2, 1? It's a vector in the direction along this axis and has a magnitude of 1. So let's think, how would we make that? Well, we need yet another vector. We need the vector r 2, 1. With a vector hat 2, 1. The vector 2, 1 is literally just, I start my chalk at 2, and I go to 1, and I put an arrowhead on it. It's the vector from 2 to 1. Okay? So that's pretty straightforward. There's no guesswork there. Positive, negative, you don't think about that. You just put your pen on 2, draw it to 1. That's vector 2, 1. That will be guaranteed to be in the direction on the axis from 2 to 1. Now we just need its magnitude to be correct. So what do we divide? Well, we divide by its length, by the displacement, r 2, 1. So that's actually a mathematical way to get that unit vector, rather than just looking at it and thinking, well, negative y. Okay? You might see in some books they might write it like this. Since this is a magnitude, they might do it like that. Go ahead and call it the vector r 2, 1 and put the bars around it. Or what we've been kind of doing is when we see nothing on here, when it's just empty on top, we know that's a magnitude. That's the displacement in this case. Okay. So now, here's the scary part. Now we're going to write Coulomb's law again for the case 2 to 1. It's going to be Ke. It's still going to be Q2, Q1. But now it's going to be over r 2, 1 cubed times r 2, 1, r vector 2, 1. See? So before we had r hat 2, 1 sitting here. So now if I bring that here, that puts another r 2, 1 in the bottom. And now it's cubed. But I have an r vector 2, 1 there. Okay? So when I write it this way, is it different? Is it some different Coulomb's law? Is it a Coulomb's law that goes as 1 over r cubed? No. It still goes as 1 over r squared. We have an r cubed down here, but now we have an r in the top. Okay? And when you cancel those out, it's still going as 1 over r squared. It's the same Coulomb's law. It's just a way to write it where we don't have to guess what r hat 2, 1 is. Okay? So let's use it a few times, and let's see if it actually does anything for us. Okay? So let's write f 2, 1 is 9 times 10 to the 9. Again, this is all MKS units, times 10 times 10 to the minus 6 squared over the separation cubed, which is 0.15 cubed. And now we just write the vector r 2, 1. Well, it's 0.15 and it's pointing down, so it's negative 0.15 in the that's I hat direction. If you multiply that out, you get minus 0.15, I'm sorry, j hat direction, you get minus, if you multiply that out, you get minus 40 j hat. Sorry. And then we could also do f41. And it's the same thing, 9 times 10 to the 9 over 0.6 cubed times, on the top we have 10 times 10 to the minus 6 squared, and then we just write the vector r41. Well, that's minus 0.6 because it's this way, I hat direction. Minus 0.6 minus 0.6 I hat. And that'll give you the same answer for that component, minus 2.5 in the I hat. And now I can tell you're massively unimpressed. It's the same thing. All I'm doing is cubing it here and then putting one up here, and they cancel. And I still had to kind of look at it to figure out which way our vector was. So really, is this any better? Okay, let's do one more part. Let's do F31. That was the difficult one anyway. Right? Let's see, F31. That would be KE 9 times 10 to the 9, 10 times 10 to the minus 6 squared over the separation. So remember the separation, it was the square root of 0.6 squared plus 0.15 squared. Before I didn't even bother with the squares and the square roots, I just wrote it down that way. But now it's not squared, it's cubed. Okay, so now to write this correctly, it's 0.6 squared plus 0.15 squared, and it's to the 3 halves. Right? It's a square root of that to the 1/2, but it's also cubed, so it's to the 3. So you multiply those, it's to the 3 halves in the bottom. And now, we don't write the unit vector, we just literally write R31 as a vector. Well, we look at our diagram, and you remember it was minus 0.6 I hat and minus 0.15 j hat. And that's it. That is your vector. If you break that down into components, solve everything, do this 0.6 squared plus 0.15 squared to the 3 halves, you'll get minus 2.28 I hat and minus 0.57 j hat. It gives the same thing we got last time. And then when you go add them up, F21, F41, F31, of course, you still get the same thing. So you see, we got the same answer with this formula, but we never did any trig. How did we do it without trig? Well, you don't always need trig. Trig is really, in this case, in a lot of cases, just a way to do ratios. There's other ways to get to ratio something out rather than having to use a tangent function or an inverse tangent to get theta. So it's really the same thing. It's just a way to do it without really having to think about the trig and the angle and the 14 degrees. We never put that in. All we had to be able to do was write the vectors R, R21, R31, and R41. So this is just another way to do it, but the most important thing to realize is this formula for Coulomb's law still goes as 1 over r squared. Okay, we have a cubed here, we have an r magnitude there. That's the main thing to keep in mind. But this can save you a lot of trouble in some problems.